Right, let's take a look at the difference between strong and weak acids and bases. We're going to start off with strong acids and bases. And the first thing we're going to do is consider what happens when we dissolve an acid in water. So a good example of a strong acid, a very common example, is hydrochloric acid. So for simplicity here, let's take 4 molecules of hydrochloric acid or hydrogen chloride and see what happens when we dissolve them in water. And what you'll notice here is that all of those molecules have ionized or broken up to form ions in solution. So because all of them have ionized, the extent of ionization in this example is full, meaning that each of those molecules has dissociated to form ions in solution. And if we want to represent this as a chemical equation, you'll note here that we're going to use a single directional arrow from left to right to indicate that all of those HCl molecules are going to break up to form H plus ions and Cl minus ions. And because hydrochloric acid is considered a strong acid, it means that no equilibrium is going to be established, which basically means the reverse reaction is not going to happen, so we can consider this as complete. So for that reason, whenever we're talking about strong acids and we want to represent those in chemical equations, we use just a single arrow. Now, some other examples of strong acids that we might come across in the course: hydrochloric acid we've just looked at, hydrobromic acid, hydroiodic acid are very similar, and then things like nitric acid and sulfuric acid. The formulas are written down there at the bottom. So what about strong base? Well, it's going to be a similar story here. Let's take sodium hydroxide as a really common example of a strong base. And again, although technically this is an ionic compound, so we'd have lots of sodium ions and hydroxide ions in a lattice, let's take 4 of those simple units and treat them a little bit like molecules here and see what happens when we dissolve them in water. Now again, you'll notice that every single one of those sodium hydroxides has ionized to form sodium ions and hydroxide ions in solution. So the extent of ionization, again, is going to be full. And whenever we're talking about full ionization and represent that in a chemical equation, we're going to use that single directional arrow to indicate that this process is complete. And again, because this is a strong base, it means that there's no equilibrium being set up because there's no reverse reaction, so we can consider this occurring completely. Common examples of strong bases are really the group 1 hydroxides, so we might see things like lithium hydroxide, sodium hydroxide, and potassium hydroxide. Right, let's now compare those with weak acids and bases and see what the difference might be. So for a weak acid, common example here might be ethanoic acid. So let's again take 4 ethanoic acid molecules and dissolve those in water. And this time you can see that actually they have not all ionized. In fact, only 1 of those molecules has ionized in solution. What do we mean by ionize? I mean it forms ions in solution. Because it's an acid, one of those ions is always going to be H+. So, considering the extent of ionization, well here we've actually only got partial ionization, or the extent is very, very small. So when I'm trying to represent this process in a chemical equation, we're going to need to use an equilibrium arrow to show that actually the forward and reverse reactions are both occurring. And how do we know that? Well, if only one of those molecules is ionized in solution, then the reverse process must also be happening, which is why we tend to have mostly in our solution the thing on the left side of the equation. And you'll notice also that in my equilibrium arrow, I've actually drawn the bottom arrow slightly bigger than the top. And this is to represent the reverse reaction as a more favourable process. Hence, while we've got lots of these in solution and not very many of those. So when we're talking about weak acids and weak bases, we can actually consider the conjugate acid-base pairs in solution and consider their relative strengths. So on the left-hand side, we've got a weak conjugate acid, which is our ethanoic acid. And therefore, if that is a weak conjugate acid, the base, or the conjugate base, must be quite strong. And if it's a strong conjugate base, that means it's quite likely to regain that H+ and end up forming my starter molecule again. So in this case, in the case of a weak acid or a weak base, the equilibrium here must lie to the left, which is why we've got lots of ethanoic acid molecules floating around and not many ions. Other examples of weak acids, we might take carbonic acid, phosphoric acid, and any organic acids, so things that contain carbon, like ethanoic acid or citric acid. They're going to be the common examples we come across. For a weak base, again, it's going to be similar in terms of the behavior. So let's take a common example of ammonia and dissolve 4 ammonia molecules in water and see what happens. And again, you'll notice here that actually only one of my ammonia molecules has reacted with water to form ions in solution. So yet again, with a weak base, we see partial ionization, meaning it ionizes only to a small extent. So, of course, again, we are expecting to see an equilibrium arrow in our chemical equation. And as we mentioned with the weak acid, if we're dealing with a weak conjugate base, to start with, the conjugate acid that it forms, in this case the ammonium ion, must be quite strong. And what does that mean? Well, that means a strong acid is going to donate an H+ back to my OH- ion to form the reactants in this equation yet again. So, as with the acid, the equilibrium is going to lie heavily to the left, which is why we get mostly ammonia molecules in my solution and only some ions floating around. Other examples of weak bases, in addition to NH3, might be things like amines, so methylamine, ethylamine, and so on. So that's the distinction there. Strong acids and bases dissociate completely or ionize completely, and weak acids and bases only ionize to a small extent. Hopefully this video was of some help.